Be here today. My name is Chen Haojia, and I'm delighted to present my work uh, titled How Small Can Xboxes Be? The design of Xbox is usually considered from two aspects. The security of Xbox heavily depends on the cryptographic properties of their Xboxes, such as differential uniformity, linearity, algebraic degree, and so on. On the other hand, the development of IoT prefers the cipher that can be easily deployed in resource-constrained devices. So the implementation cost of Xbox, such as the area or latency, needs to be as small as possible. Currently, there are two active research hotspots about Xboxes. One is constructing new Xboxes, another is to optimizing the existing Xboxes. And I will introduce them both. The previous method to construct Xboxes can be mainly classified into three types, and type 1 is to choosing an Xbox from equivalent categories. In 2007, uh, the Linder and the Postman classify all the optimal 4-bit Xboxes into 16 CCZ equivalence categories. And in 2015, and Wentao Zhang further developed this classification as 183 categories based on the bad input and bad output. The type 2 is to using a mathematical method or special structures, combining the affine transformations and the inverse function of a finite field to construct Xbox is a typical mathematical method, just like the Xbox used in the AES. And for the purpose of Xbox with low implementation cost, some special structures such as Fistel, Misty, Bridge are also widely used. However, these design strategies depend on structures, so it's difficult to reach the minimum area. Type 3 is to solving out an Xbox by automatic tools. Zhenyu Lu et al. Propose an automatic search method based on SAT, which can take multiple cryptographic properties into consideration. However, algebraic degree is not covered in this method. Meanwhile, the implementation cost is not considered yet. Previous work on optimizing the implementations of existing Xbox available are very few. In 2017, Jin et al. Proposed an automatic tool lighter to optimize for small area circuits for existing Xboxes. They used a graph-based meet-in-the-middle search algorithm under the assumption that every instructions are invertible. Next, in FSE 2016, Stoffelen transformed the searching Xbox implementation into SAT. With an SAT solver, author can optimize the Xbox's smallest number of gates. And then, based on the Stoffelen's work, Lu et al. Improved Stoffelen's model, which can which applied proportional quantitative constraints to the area of each logical gate, and they try to find optimized implementation for existing Xboxes with smallest area under certain standard cell library. Combining these two research directions mentioned above, we can naturally think of these questions. Can we simultaneously constrain the cryptographic properties and their hardware implementation? And second is how to consider the area and the gate depth complexity simultaneously. And next is, can we cover the constraints on algebraic degree? Uh, then what's the minimum area of all 4-bit S boxes? The last one is how to, for the larger scale of S boxes, can we optimize the area of it? Then in this paper, we propose a model to tight bounds on minimum area to construct S boxes. Uh, first we propose a prim-like gradient algorithm to tighten the upper bound of minimum area to construct S boxes. As we know, each S box coordinate function is composed of a certain number of logical gates. Meanwhile, different coordinate functions share some of the same gates. Here we transform the construction into a minimum spanning tree problem under graph theory. In this graph, the edge represent the logical gate, and the weight of each edge represent the area of every logical gate. And the vertices represent the input state or the output state of corresponding logical gate, which can also be considered as Boolean functions. We construct a minimum spanning tree of all logical gates to implement the S-box in a step-by-step manner based on a topological structure. During the construction of each Boolean function, we need to ensure that the state of each terminal vertex satisfies the property of the S-box Boolean function. First, we use area as the objective function and iteratively add edges and vertices to the connected graph to construct the first Boolean function. Then, based on the existing connected graph, you can see on the picture B, we continue to add edges and nodes with the goal of minimizing area until the second Boolean function is constructed. This process is repeated in picture C and picture D until all the Boolean functions of Xbox are built. In this way, we can obtain a locally optimal solution for the area of Xbox, which can also be regarded as an upper bound of area. And for the lower bound of Xbox area, we relaxed the constraint conditions on the Boolean function of Xbox. We only require each Boolean function to be balanced. By using the balance properties of a Boolean function, which is property 1 and property 2, we determine that the area lower bound for implementing two Boolean functions of an Xbox is 6GE. And consequently, we established that the area lower bound for implementing a whole 4-bit Xbox is 9GE. And through our two methods for searching the upper bound and the lower bound of Xbox area, we significantly reduce the search space for the below search. And next is in the previous work, there are two different automatic search model of Xbox, which are the model of constructing Xboxes and the model of optimizing existing Xboxes. We found that the variable in the above two models are independent. So it is impossible to bridge the gap between them. So by merging the two previous models, after we merge after that some challenges have arisen. There are too much model variables, making it unfeasible to run the model. So we need to provide more concise constraints of edge boxes. And firstly, we add the constraint of algebraic degree. However, it's difficult to construct ANF in SAT model. To solve this problem, we can via SOP expression. The SOP expression is a way of representing all input combination that make an output of 1. It's a logical expression derived from the truth table. Simply speaking, we need to firstly identify all the input combinations that result in output of 1. Secondly, expressing each of them as a midterm Boolean function. And finally, connecting all logical operations to form a disjunctive normal form. And in the definition, the GUX is the midterm Boolean function. And after that, we need to transform SOP expression into ANF expression. From the definition of SOP, there are 2 to n different midterm Boolean function GU. Multi. Therefore, the disjunctive OR in fx can be directly transformed to the sum. And based on this, we expand fx and extract the coefficient of each term in the expression. And finally, we obtain the ANF of the Boolean function. And now all the coefficient in ANF of fx can be expressed into SAT model since all the alpha can be pre-computed. After obtaining the ANF constraints, we need to impose restrictions on the algebraic degree. In other words, we need to constrain the coefficient of the term 0 with the degree greater than d, and the coefficient of term is 1 with the degree equals to d. Next, our paper proposed a method of reducing the search space to accelerate search. Before that, I need to briefly introduce the model for optimizing Xbox implementations. Each logical gate have several inputs, and each input must be either an input bit of the Xboxes or the output of a preceding logical gate. Taking a 4-input gate as an example, we use the Q to represent each input bit of the logical gate, and the X to represent the input bits of the Xbox, and T to represent the output bit of the logical gate. So the constraint on ABCD in the following expression is used to indicate that each input of the logical gate can only take 1 bit logical gate. For each output bit Y of the Xbox is similar to the above. So we found that when using 2-input and 3-input gates from a specific logical gate set, like the observation one, the output of each gate is not affected by the order of the inputs. And we add constraints on the order of inputs of each logical gate in SAT like below. Besides that, for since two Xboxes with the same bit permutation equivalent class share the same cryptographic property and the area, it's no need to distinguish the order of output bits. So we fixing the order of output bits of Xbox. In addition, we simultaneously constructed constraints for gate depth complexity. We set the gate depth of each input bit of Xbox to be 0. Then we impose constraints on the gate depth of each gate. For example, for a 4-input gate, the gate depth is defined as the maximum gate depth among its 4 inputs, and then we will plus 1. So that's the gate depth complexity model. As an application, we apply our model to all 4-bit Xboxes, including all cryptographic properties. We search for the lower bound of 4-bit Xbox area under different standard cell libraries. Taking the UMC 180 nanometer library as an example, when using 2 input and 3 input gates, the area lower bound for 4-bit Xboxes is 12 GE, and when constraining no fixed points, the area lower bound becomes to 12.33 GE. And after introducing the 4 input gates, the optimal 4-bit Xbox area lower bound is reduced to 11 GE. And for all 4-bit Xboxes, it's reduced to 9 GE. Besides, our model can also be applied to optimize the area of larger scale existing Xboxes. For example, the optimized area of Ketchup Xbox is reduced to 17 GE, which is smaller than the optimized result of 17.6 GE in the past. And for 8-bit Xboxes, we optimize the area of skinny 128 Xbox. The optimized area of skinny Xbox is 26.67 GE, better than the 29.33 GE in the design documentation. And last, to summarize our paper, we firstly propose a Prim-like greedy algorithm to tight bounds on minimum area to construct Xboxes. Then we constructed an automatic search method for Xboxes, which simultaneously consider cryptographic properties, area, and the gate depth. And finally, using the search model, we determine the minimum area of 4-bit Xboxes and can also optimize the area of larger scale lightweight Xboxes. Thank you for your listening.
Thank you, Chen Hao. Are there any questions? Mustafa?
Slides. This slide. Okay. I can hear.
Okay. So was the comparison to Skinny on the same library, and related to that, did you actually try yourself your Xbox without optimization and then compare to your result or no?
Pardon?
So
Sorry.
did you try to implement the Xbox without optimization using the census tool and then compare to your result, or you just rely on the Skinny paper?
Yeah, The 29.33 is the skinny documentation, documentation area, and besides that, we synthesis the S boxes for our method and the documentation matter, and the result is the same.
So you did both yours and the original one for census.
Yeah.
Okay, thank you.
Okay.
Are there another questions?
How did you do the synthesis? Using the compile ultra flag or no?
Uh,
Did you use synopsis? There's an extra compile ultra flag which optimizes for area. Did you use that or did you?
we don't optimize in the synthesis part. We just optimize in the logical.
Okay.
In the logical and yeah.
Okay, let's thank the speaker again.